Okay, students, so in this group we're going to be going over integration by parts. So we're going to be doing the derivation first, and then we're going to try out an example. All right, so what is the integration by parts formula? Let's start out by writing what the formula is. The integration by parts formula is given by the antiderivative of um, u dv equals uv minus the antiderivative of v du. Okay, so this is a integration by parts formula. All you just need to do is find out what u and dv are, and then use it to find du and v, and then you set it up like this. Okay, so there you have it. So where on earth did this formula come from? That is what we're going to be determining in a minute. Let's not forget our constant for c. All right, so let's do the derivation first, and then we'll try out an example. Okay, on subsequent clips I'll do more complicated examples um, for you to gain more mastery of the whole concept. So derivation, where on earth did this formula come from? Well, it's an offshoot of the product rule. So from product rule, we know that for two functions, let's say f of x, let's call f of x equals u, and g of x equals v. I like to use these letters because it's easier to work with and it's consistent with what I want to derive. We know that, so for this function we know, what do we know? We know that the derivative of the product of the two functions, ddx of f times g, which I'll write as uv, okay, for symbolic convenience here, is equal to u dv dx plus v du dx, right? So that I know that from the product rule, okay? So what I'm going to do next is I'm going to use that to find out what I'm going to basically anti-differentiate both sides, okay? So let's go ahead and anti-differentiate both sides. And out all this here. So if I anti-differentiate both sides, what's that going to give me? So on the left side, I take the antiderivative of the whole thing, for 9 yards over here, and then on this side I just take the indefinite integral of this sum right here. Okay, so what's that going to give us? Hey there students, on this clip we're going to be going over integration by parts. So let's start out by writing down what the formula is. I'll go over the derivation and then we'll apply it to an example, okay? So let's write down the formula first. Formula. So the formula for integration by parts is basically the antiderivative of u dv equals uv minus a indefinite integral of v du plus c. Okay, so there goes the formula. So question is, where on earth did this formula come from? So let's go over the derivation first, and then we're going to start looking at examples. Okay, so derivation. Now, this formula, believe it or not, is a modified version of the product rule. Okay, so let's write this down from the product rule. From the product rule, um, we know that we know that if if two functions, let's spell that properly. If two functions are f of x. Let's say f of x is u, and g of x is v. Then the product rule tells us that the derivative of the product, I'm going to use u and v, okay, for symbolic convenience, and it's more consistent with the formula I seek to derive. So v dx of the product of the two, uv, is equal to u dv dx plus v du dx, right? So how can we get the integration by parts formula from this? What I'm going to do is, first of all, multiply everything by dx to get rid of the denominator. So why don't we multiply everything by dx? Okay, on the left side, multiply this by dx. And on the right side, I will multiply each term by dx. Oh, that doesn't look good. So how about I multiply this whole thing by dx, okay? Dx will be distributed to both terms on the left side, on the right side, okay? So on this side, you can see this cancellation action happening here. And then when this is distributed to both of them, you have the same cancellation action happening. So what that essentially does is it clears out the dx's at the denominator. So we're going to have d of uv equals u dv plus v du, okay? So now, now that we have this, I'm going to anti-differentiate both sides of my equation, alright? And then let's see what we get as a result of that. So if I take the antiderivative of this piece right here, and then times the antiderivative of this entire piece, what's going to happen on the left side is that the antiderivative and the derivative are inverse operations, so they basically cancel each other out. And on the right side, you're going to be left with uv, and on the right side, the antiderivative gets distributed to both terms, right? Term by term integration, as you've heard before. So it's going to be the antiderivative of u dv plus the antiderivative of v du. All right, so there goes what you get. Now, in order to make it consistent with my integration by parts formula, all I just have to do is isolate u dv, right? If I can isolate u dv, then I'll be done. So how do I isolate u dv? How about I just subtract v du from both sides, right? So on the left side, I subtract the indefinite integral of v du, and then on the right side, the same story, okay? v du. So I'm going to be left with, using the reflexive property of equality, the antiderivative of u dv equals uv minus the antiderivative of v du. And there goes your integration by parts formula. Okay? So there you have it. Alright, now having derived it, now let's try out an example. I'm going to do an easy one in this clip and then more complicated ones in subsequent clips, okay? So example 1, evaluate. We're going to be evaluating this integral. Evaluate the indefinite integral of e to the x sine x dx. Okay? Uh-oh. E to the x of sine x. Alright, now for this one, let's we have a formula up there to guide us. So let me just rewrite it on the side up right here. Antiderivative of u dv equals uv minus the antiderivative of v du. Okay, so in this piece I have two functions here. One of them is u and one of them is dv. Which is which? Let's see. There's a rule that can help us to easily identify what u is, okay, and then the other will be dv. So it's called the Lipet rule, Lipet. Okay, so this is the order of the selection of u going from top to bottom, okay? L means logarithmic functions. Logarithmic, let me write down for you. I is inverse trig. P is power. E is exponential functions, and then T is trig. Okay, so this is the order of selection of for u. Okay, So we have an exponential function here, exponential, and a trig function here, trig. But in this continuum, e comes before t, right? So exponents trumps trig or sine. So guess what? Our u is going to be e to the x. Okay? So if our u is e to the x, then um, then dv is going to be sine x. Sine x, to be more specific, dx. Okay? So take a look at this. This piece right here is my u, and this entire component right here is my dv. So that matches with the u and the dv on the left side of the integration by parts formula. Okay, now that I know u and dv, I need to find v and du. So let's look for du first. That's easy. So du is simply the derivative of e to the x. So du is on the derivative of e to the x. What's the derivative of e to the x? It's simply e to the x, right? And then v, to get v, we've got to get rid of this d. So inverse of derivative is the antiderivative, right? So all we just have to do is integrate, find the antiderivative of sine x, and that would be what v is. So v is basically the antiderivative of sine x, right? Dx, which is simply negative cosine x. Okay, so there you have we have v now, and then we have the u. So all we're going to do is we're going to pull all these four ingredients together to generate this equation right here, and substitute into this equation right here. So the antiderivative of u dv is simply going to be the antiderivative of e to the x sine x dx, this is the original question, equals uv. See this diagonal right here? The diagonalization is basically what creates uv. Important to note how the diagonal is working, because this whole idea of going diagonally will help you master another technique of integration by parts known as tabular integration. Okay, that's coming up in subsequent videos. So uv, you just multiply these two, is going to be negative e to the x cosine x, all right, minus the indefinite integral of v du. So v is negative cosine, so negative cosine x times du. Du is e to the x. Sorry, I forgot to put dx right here. Dx. Okay. All right. So it's gonna be minus cosine x. So this is v. Du is e to the x dx. Okay. So let's do some window dressing and make this look nice. So this is basically going to be the antiderivative of e to the x sine x dx equals minus e to the x cosine x. This minus multiplied by that one becomes plus antiderivative. The standard way of writing this is the exponential function first, and then cosine x dx, and don't forget your critic constant for c1. Okay. So we've just done the first step for the integration by parts, but we've ended up with a function that's similar to what we started with, which is an exponential function and a trig function. These type of functions are integration by part babies. That's the main way you can integrate them. So this is a situation just like the original problem where you have a trig exponential function and a trig function. So to evaluate this, you have to use the same method as what we did before. Okay, so we're going to do integration by parts again on this piece. Okay, so now let's refresh our memories by writing down what the integration by parts formula is on the side right here. So it's basically the antiderivative of u dv equals uv minus the antiderivative of v du. Okay, so let's do this. Focus our attention on evaluating this integral right here, and then we're going to use it to, we're going to put it back in. Okay, so I'm going to do this piece in blue. So I want to find antiderivative of e to the x cosine x. Okay, we've created a new problem for ourselves. So all right, let's do this. So for this one, I need to know my u and my dv, right? Because u and dv are the left side of the equation. So How do I select it? Remember LIPET? LIPET says that we follow this continuum to select u. Exponent comes before trig, right? So this is my u. Okay, don't forget. And then my dv is going to be the other one. So if this is u already taken off, dv has to be cosine x. Okay? Alright, now we're going to use these two pieces of information to find v and du. Okay, so du is easier to find. Du is simply the derivative of e to the x, right? So this one is going to simply be e to the x dx, just like we had before, up here, similar. And then to find v, we just anti-differentiate cosine x dx, right? So what's the antiderivative of cosine x dx? It's sine x, right? So sine x. Alright, so there goes your v. Now we're going to put it together. So this antiderivative for cosine right here is basically going to be, so antiderivative of e to the x cosine x. Well, what we can do is instead of rewriting it, I can plug it in straight into the problem. You know what? Let me write it in blue. Okay, I'm making it a little bit longer so that you can really understand what's going on. So this piece right here, the antiderivative of e to the x cosine x dx, is basically going to be uv, which is e to the x sine x, okay, minus the antiderivative of v du, which is going to be e to the x sine x, okay, dx. Now, you see what I just did here? I just used this formula just for this portion. Focus just on the blue area right here, okay? This is my second integration by parts. So uv together to create this, e to the x and sine x. And then v du, I just use this one and this one together to create v du, okay? Now guess what? I'm going to take this whole argument right here and I'm going to plug this whole thing into this piece right here, into this, okay? So that's what I'm going to do next, since I already know what this is. So now let's rewrite it. So it's going to become, right, we're now going back to the main problem. So we're going to have the antiderivative e to the x sine x dx equals negative e to the x cosine x plus, now let's write this down. Oh yeah, sorry, there's supposed to be a c2 somewhere here. So this one has its own c2. So let's put it over there. Don't forget the pretty little constant. So plus this piece, e to the x, e to the x sine x minus the antiderivative of e to the x sine x dx plus c1 plus c2. Okay? So now if you notice, if you look at this integral right here, you notice that this term right here is the same as this term right here, okay? So this term and this term are the same. So you know what I'm going to do? I'm going to combine them together, okay? I'm going to combine both terms. So why don't I just simply add the antiderivative of e to the x sine x to both sides to see what happens? So I'm going to add the antiderivative of e to the x sine x dx to the left side of my equation, to the right side of my equation, and also to the left side of my equation, okay? And then that gives me, on the left side, double this, because you're adding it twice, because like there's a 1 here, there's a 1 here, so you're adding it to itself, so it's going to be double that, yeah? Because like x was x is 2. In this case, x is this antiderivative and the antiderivative, right? 2x. You get the drill. Anyway, so I'm adding something to itself, so you get double. So you're going to have 2 e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. And then we can just say c1 plus c2, let's just call that c. Doesn't really matter, it's just a constant. Okay, like that. Almost there. Remember, the question asks us just for this piece, not twice of what it is. So in order to finish this off, all I'm just going to do is multiply both sides by 1/2, right? Or divide both sides by 2, whichever way you want to do it. So I will multiply the left side by 1/2 to get rid of this 2 here, so not me. And then I multiply this whole thing by 1/2. So we're going to be left with antiderivative of e to the x sine x dx equals 1/2. See, this, I can, it doesn't matter. I can just write it as, I can switch these two around if I want. It doesn't really matter. I can say e to the x sine x minus e to the x cosine x, just to make it look nice, plus 1/2 c. Okay, like that. This we can call this constant c3, 1/2 c3, and then I don't like using indices here, so I can just let c3 be c. So final answer, antiderivative of e to the x sine x dx equals 1/2 e to the x sine x minus e to the x cosine x plus c. Okay, you can call this c1 plus c2 plus, 1/2 c1 plus c2 or 1/2 c3, or just c. It makes no difference. Okay, c is just some integer, some constant value. All right, so basically that's it. That's your solution right there. Thank you so much for paying attention to this presentation. Please subscribe to my videos for future updates, and if you need help on specific concepts, you can always feel free to request a video. And then if you want to see the collection of my clips, you can simply go to mathgoodserve.com and view whichever clips you want to see. All right, thank you and have a wonderful day.